So today's video is part 3 of a 3-part tutorial on thermodynamics for General Chemistry 2. And today we're going to talk about coupling reactions. In a coupled reaction, I want you to be able to find the resulting entropy, the enthalpy, and the free energy. I want you to know the relationship between free energy and the equilibrium constant K and the equilibrium reaction quotient Q. And I also want you to be able to find the instantaneous free energy at any time as a reaction proceeds away from standard conditions. So we'll start by reviewing the reaction we ran in the second video, where we basically decompose copper oxide to make solid copper and release oxygen. And you can tell from the calculations we did then that the delta G for this reaction is positive 129.7 kilojoules, which is not spontaneous at 298 K. But if you're motivated to turn that copper oxide into solid copper to recover the copper for resell, you might want to somehow be able to run this reaction in a spontaneous method. So there's a method called coupling, which we've really talked about already in kinetics and some in equilibrium, where basically you can take two equations and put them together. So in this case, we're going to take copper oxide, the decomposition, and we're going to couple it with the oxidation of carbon to carbon dioxide. And if you'll couple these two reactions together, so remember this is adding reactions. I had a half O2 up here on the first reaction, so the second reaction had a full equivalent of O2, so we're going to cut it in half. And we remember that, look, if I multiply this piece of the equation by half, I got to multiply it all the way through. So consequently, you're able to add these reactions, and then you can cancel out what's common in the first two reactions. And once you do that, you just collect all of the reagents, the reactants, and the products. And what you have is a reaction that says, look, you can couple copper oxide with carbon, and you can make pure copper, and it'll release CO2. Now, if you look at this from a redox perspective, you can do the oxidation numbers on copper connected to a -2 oxygen. This must be a +2 copper, copper 2. Go over to the other side, the copper is now 0. So this must have gained electrons. That's reduction. And by the same token, if you look at the carbon fundamental element, starting off its oxidation number is 0. And you get over here, and carbon dioxide, its oxidation number is 4. So the carbon started at 0 and went to a +4 oxidation number, which means it must have undergone oxidation. And so although this is cut in half, so that would be 2 electrons, there was also 2 electrons exchanged. Now this is something we've done with Hess's law in the first General Chemistry 1 in the past. But I just want to remind you that when you have a reaction like this that you couple, it's not just a theoretical exercise. Hess's law sometimes appears that way. It's actually an actual application you can make, where you literally take copper oxide and then you mix it up. So I've got my little blue copper oxide, it's probably really black. Mix it up with carbon, which also is black, and you mix it up really good, and then you give it just a little bump with some activation energy. So we put it over a burner for a minute, and that will kick that off, and it'll literally create copper and release CO2 gas. So that is the reality of this, and in order for this to happen, you have to have this carbon in intimate contact with the copper oxide so the electrons can be exchanged. This is a real way to make pure copper from copper oxide, and it's something we do here in our school in the lab. All right, so let's see if this is beneficial to couple these together. Look at it from the thermodynamics number standpoint. And as I've advised you in past videos, just line up your table using each of the reactants kind of as a template. So I go to my thermodynamics table and get my figures for the copper oxide. Remember, it's a reactant, so it's going to have a change of sign on it. The same thing for its entropy. The carbon also is a reactant, so it gets a change of sign on it. The copper is one of the products, so it remains the same. And remember to multiply through by the coefficients. So now I can just use this table as is and just sum across, and I'll actually have the heat of reaction and the entropy of reaction. Heat of reaction is 40 kilojoules. It releases energy, which is favorable to spontaneity. And it also increases in entropy, so that also is favorable to entropy. So this is the kind of situation that's spontaneous at all temperatures. But just to check that, what we do is we basically calculate the free energy, taking the enthalpy minus the temperature times the entropy. And remember, in entropy, when you get it out of the table, it might be in joules, so I want to convert it all to kilojoules, or vice versa. But anyway, I do this calculation and see it is indeed a negative entropy, which is spontaneous. And now just to go look for the crossover temperature, remember, you can always take the enthalpy divided by the entropy, and you should be able to look at a crossover temperature. Whenever you do this calculation and you get a negative temperature, that's your red flag that it's either spontaneous at all temperatures or never spontaneous at any temperature. In this particular condition, though, we know that both of these thermodynamic parameters are favorable to spontaneity. So this is a way to couple the reaction, and it does prove that it can make it spontaneous. Now I just want to show you another cross-check. This is good for you to know. Let's just say that you had actually worked out you'd gotten out the thermodynamic parameters for each individual reaction. So I kind of did this a little differently over here. I just went along and found the enthalpy, the entropy, and the free energy. And I just did worked my way along and did for this particular reaction, here's all three thermodynamic parameters. And for this particular second reaction, here's all three parameters. And actually you can call these steps like we learned in kinetics, and that's actually appropriate. Okay. And I just want to show you how that when you have thermodynamic properties like this and you're adding the equations, you literally just add the thermodynamic parameters. So 157 minus 197 is a minus 40 kilojoules per mole of heat released in this reaction. You add these two, and that confirms the other way we did it. Now we add these together, get 0.10 kilojoules per Kelvin. That's the entropy, and that jives with what we calculated here. And then the free energy you can also just sum up, and it also is confirmed by the other calculation. So you always kind of have a lot of different ways you can go at this. But the take home here is when I add steps, the thermodynamic parameters are added. So now I just want to remind you of some skills you'd learned in General Chemistry 1, and we kind of reviewed them a little bit when we were doing kinetics and equilibrium earlier in the videos. But when you are trying to take steps and rearrange them such that they match the overall equation so that you can figure out how these thermodynamic parameters combine, I just want to give you a technique and just remind you again how you do that. You start with the overall equation, that's the key. And you just work left or right on the overall equation. So the first species I come to is the dinitrogen oxide reactant. And when I search down here in my steps, I see that, okay, here's dinitrogen oxide, but the problem is I have two equivalents as opposed to just one. So I can make that adjustment, right? So I'm going to rewrite it down here. I'm going to make the adjustment by multiplying through by half, which I did on the equation, right? And that means that I have to take my thermodynamic property and also multiply through by a half. Then I go back and I work on my next species that shows up as a nitrogen dioxide reactant. And I look down here and say, oh, that's in the first equation, but the problem is that nitrogen dioxide is in a reactant here, so I need to actually flip this whole equation over. So now I've taken this, flipped it over, and that's the other issue with it. It looks like is it has too much in NO2, but we'll deal with that here in a second. So I take that, and the point being, whenever you flip an equation, the thermodynamic parameters just change signs. Now I multiply through by the half to get that to the right place, which means I got to multiply through by the half on the thermodynamic parameter. And then last but not least, this third step, I could put it in just to cancel out things that aren't found in this reaction. And in order to do that, I don't really need to change a thing. So consequently, the thermodynamic parameters remains unchanged. And now I just walk my way through and cancel things that are common to both the reactants and product side. So starting with N2, I've got N2 on the left. I've got two N2s here on the right, but it's been cut in half. So that is equivalent to an N2, so that'll cancel out. I've got one O2 here. Over here I have a half O2, and here is another half O2, so those two together will cancel that. Two halves makes a whole, so that cancels. And then I just collect what's left over. Now it's half of 2 NO2, so that's NO2. Get over here, I've got, it's a half of 2 NOs plus 2 NOs, that makes 3 NOs. And then half of 2 N2Os, that's N2O. And so I have indeed ended up with the original target equation. So at that point I know that I can just collect these. Now, how do you add thermodynamic parameters when your equations have been added? You just sum them straight down. Include the adjustments you did with coefficients and change in sign. So overall, this reaction is has a positive free energy, which means it's not spontaneous. But more importantly, that you learn these skills of manipulating equations. So what are the keys here? Work left to right on the overall equation. If you multiply through on the equation, you also need to multiply through on the thermodynamic parameter. If you reverse an equation, then you need to change the sign on the thermodynamic parameters. And then when you add steps in the reactions, in the equations, the results are just the addition of the thermodynamic parameters for each step. So that's what we did. Now I want to point something out, and you'll have to look back in these sections to remember this, but it's just a good time to kind of compare and contrast. When we did kinetics and you have multiple steps, all you have to do is focus on the slow step, and that is what determines the overall K. All right? When you look back at equilibrium, remember equilibrium is a multiplied constant. So whenever you're adding the equations, the K's actually multiply. You go up one order of operation, right? So whatever you do to the equation, you go up one order of operation, that's what you do to the K's. So we added the equations, we need to multiply the K's. So that's just a good reminder and worth looking back so that you keep these three things separate whenever you're adding reactions. So I'm going to give you an opportunity to practice. I'm going to ask you to determine the free energy for the reaction at 290 K, in which solid calcium carbonate decomposes to form solid calcium oxide and gaseous carbon dioxide based on the following two formulas. So the overall equation is actually given in this narrative. And so from that overall equation, you should be able to stack these two equations such a way that they'll cancel and give you the overall equation, and then you'll know what to do with the thermodynamic parameters. And then the next question is, when you figure that out, is the reaction spontaneous? Is there a crossover temperature for spontaneity? And cross-check your answer to A with work from B. Now, when you go to figure out the crossover temperature, you'll probably need to pull out your fundamental thermodynamic tables out of your book and do calculations within the overall equation. All right, so stop your video, try and solve this problem. When you're done and you want to check your work, you can just restart the video. All right, let's see how you did. First off, let's just turn this narrative into a reaction. We got calcium carbonate. It's decomposing, so they're yields, and it makes calcium oxide, +2, -2, so it's 1 to 1, and carbon dioxide in the gaseous form. All right. So now what we need to do is we need to reorder these equations such that they equal this overall equation. So once again, work left to right across the overall equation. So we're going to start with calcium carbonate. So now calcium carbonate's in here, but it's on the product side here. It needs to be moved to the reactant side. So we're going to flip that equation. And remember, once you flip that equation, it's going to change the sign of your thermodynamic parameter. All right. Then the next species we come to is the calcium oxide product. That is found as a product in here, so that meshes. It's just 2 equivalents and only 1, so I need to multiply through by 1/2. If I do that to the equation, I need to do the same to the thermodynamic parameter. Then I can get in here and just sum up the equation, see if everything cancels that I need to cancel. So if I apply 1/2 times 2, that's 1 calcium. That'll cancel that calcium. And then if I apply 1/2 times 1 oxygen, that's half an oxygen, which that should cancel just fine there. And now you can see here's all that I'm left with, this calcium carbonate becoming calcium oxide and CO2. Now remember, this 2 has been multiplied by the 1/2, so that's why it's 1. And then, because this is canceled and yielded the overall equation, I know that my thermodynamic parameters can now be just summed as they're written here. So I'm going to have to take half of this negative free energy. And so I've now taken the free energy and lowered it some, but it's still positive, so this is still not a spontaneous reaction. So now that raises the question, I wonder if there's a crossover temperature somewhere else, because this assumes standard conditions at 298 K. So once again, I always advocate the method of just using your balanced chemical equation as a template. And we need to find the heat of reaction. We're going to go ahead and find the delta G, since we have our thermodynamic tables out anyway, and we can confirm what the number we had just calculated. And last but not least, we're going to do the entropy. And remember, entropy off the tables is in joules, so we need to convert it to kilojoules or convert these back to joules, whichever you prefer. Just stay in the same habit would be my recommendation. All right, so we get out our standard table from a book or a handout in class. And remember that this is a reactant, so it's going to have a sign change when you actually do the calculation. Do that all the way through. Get over here and look up calcium oxide. It's the sign remains the same. Move the decimal over 3 times here for the entropy. Calcium carbon dioxide is a product, so no need to change the sign. Enter it, convert. Now you can just sum across. You get the heat of reaction is 179, so it is endothermic, which isn't favorable to spontaneity. The Gibbs energy is 132 kilojoules, which is nice. That's comparable to what you had done with the other calculation with your plus or minus there. And then the entropy is actually slightly increasing. Now that gives me some promise, because if your entropy is increasing, you can control that with temperature. So there must be a crossover temperature in here. So let's find the crossover temperature by applying the enthalpy by entropy equation. You plug in 179 and 0.16, and you see that at 1,119 K, you can raise the entropy enough that it makes the overall equation spontaneous. So above 1,119 K, the reaction is spontaneous. Now, question 3 asks you to cross-check your work. And so already we've done this and seen that this 132 and 131 are close within the precision of our calculations. Okay. And then last but not least, if you want to do free energy another way, you can take your equation where the enthalpy minus temperature times the entropy should give you your free energy. So I've basically taken these two numbers, plugged them back in at 298. I see 131, and that matches. So there's just a couple double checks. Okay, so what you've seen so far is that the size and the sign on the delta G, you know, if you know it's positive, it's not going to be spontaneous. If it's negative, it's spontaneous. The larger the number is, the more spontaneous it is. So this reminds us of looking at equilibrium, because remember, when the equilibrium constant's large, that's indicative of favoring going to products and vice versa. So we think those two should be related. So just in a qualitative sense, we know that when K is greater than Q, and when delta G is less than 0, then the reaction is going to proceed towards products. And we know that when the Q is greater than the K, or the delta G is greater than 0, then the reaction is going to proceed towards reactants. And then we know that when Q is equal to K, when you've reached equilibrium, right, and delta G is 0, right, you're at equilibrium, the reaction in essence has stopped. There's not free energy to harvest. The qualitative relationships you need to understand. But for quantitative calculations, this is the relationship between free energy and the equilibrium constant at standard conditions. All right? And remember, once again, standard conditions for gases are at 1 atmosphere, and for solutions are at 1 molar. So for example, I have this reaction here. The free energy at these conditions, if I was to do the equilibrium on it at standard conditions, that would be relative to 1 mole of A, because in the balanced equation there's only one equivalent of A, or for 2 moles of B. Now if you need to calculate the free energy at any concentration in the reaction, so as the reaction goes on, right, remember we've learned in the past, hey, equilibrium can be adjusted from standard conditions to any concentrations by using this concept of Q, which is the concentrations at any time. So once again, this looks very similar, but you do a little adjustment. You start with a standard state free energy, and then you make an adjustment, RT log of Q. And I want to remind you that in this case, R is the 8.314 joules per k-mole. So at equilibrium, Q equals K and delta G equals 0. So if you wanted, just to see where these derive from each other, if I took this original equation and I plugged in and say, okay, let's look at the equilibrium condition. That's where delta G equals 0, right? So it at that point is the delta G naught plus RT log of K, right, should equal 0. And now if we just solve, isolate delta G, subtract out minus RT log of K to the other side, voila, you get back to here, and this is why these two are related in this way. Okay, so just a couple comments. Free energy number, whatever you see as a free energy number, that is the energy that's available to leave the system. Sometimes that'll help you remember that it's leaving the system, so it's available to do work. That's why there's a negative sign on it. And so when you see a free energy of negative 3.5 kilojoules per mole, that means there's actually 3.5 kilojoules a mole available to turn the wheels or raise a weight. The fact that this has a negative sign on it is not meaning that it's less than 0. It gives it direction. It means it's leaving the reaction. Then as the reaction proceeds, the free energy will continue to approach the positive number until the system reaches equilibrium. At equilibrium, the available free energy is gone. It's equal to 0. Okay, so now we've looked at ways to calculate the free energy at any time as a reaction proceeds. So we're going to do a little practice problem here where we we react iodine with chlorine to make an iodine-chlorine molecule. And so here at standard conditions, we know that the equilibrium, the Kp, these are all gases, so we'll do Kp here, is 81.9. At standard conditions, 298 K, which means that all of these are at 1 atmosphere. Okay, so at that conditions, can you find the free energy? Then what will happen when it goes down to equilibrium? It's going to run until the concentrations adjust. And then finally, I want you to do a calculation somewhere along the way. And so if we start at standard conditions of 1 all the way across, and I start losing some iodine pressure down to 0.9, which meant I lost 0.1 atmosphere, and this must have gained twice that much, or 0.2 atmosphere. Okay, can you calculate then what the free energy is under these partial pressures? So stop your video, try and solve the problems. When you're ready to check your work, restart the video. Okay, so let's see how you did. So when the reaction is at standard conditions, you basically use the equation where the free energy equals negative RT log of K. So it's just kind of plug and chug. The only caution I give you is remember that R is in joules per mole K, so consequently your final answer is going to be in joules, and it's going to look large, but remember when you look at free energy in a table, it's usually reported in kilojoules. So you just have to move the decimal over 3 times and you'll see an equivalent answer if you had done it by comparison on the table. So when the reaction is at equilibrium, the free energy is 0, and that's just a concept that's always true. And now the last problem is what happens when you get to these non-standard state conditions where you have these different partial pressures. And for that you need the equation. Start with your free energy, which we just calculated, okay, in step A. Add RT log of Q, and remember Q is products over reactants, and remember to include the coefficients. So now you just basically plug and chug, and remember when you do this calculation you take the free energy standard state conditions which you calculated in part A of this problem. I'm going to leave it in joules because basically we are working with R in joules. The K's cancel, and then basically the Q is found by taking the products. In this case, it's the iodine-chlorine molecule, which is raised to the second power because of this coefficient, and divided by the 2 reactants, which are both at the same partial pressure. So you plug and chug and you end up at negative 9,475 joules per mole. And I just want to remind you, you started off at a free energy of almost 10,000 joules per mole, and as the reactions proceeded, we figured out we started out standard state conditions, and so you've dropped 0.1 atmospheres of partial pressure. And as you proceed along the reaction path, then the free energy should be approaching 0, getting more positive, and that's what happened. So with this video, we close up our section on thermodynamics, and I hope this has helped you understand how to couple reactions and how to find Gibbs free energy at any time in a reaction, and also reminded you about adding reactions and how it's going to affect the consequent calculation of these thermodynamic parameters.